3 chapters remaining on this book. Yesterday I was talking to some friends about the progress that I made on it because it's a big book and I feel accomplished, but it's kind of like a marathon getting through this. Whenever I run a marathon, in my mind I always imagine it's like 2 to 5 miles more than what it actually is, so that I'm just mentally prepared to just cross the finish line and keep going if I need to. Inevitably, when you cross the finish line, you just crash. At least that's been my experience. I kind of feel like reading this book has been the same, where with the marathon, if I don't imagine that I need to continue running past the finish line, I'll stall out on that last mile. That last mile is really the place where a lot of people stall out, and I feel like that's happened to me on this book. The last mile, I've kind of like stalled out. I was like flying through so much material, and then I got to these chapters. I think it started happening before sockets, but definitely when I hit the sections on sockets, I just kind of stalled out. And yeah, to be honest, my motivation on it has kind of gone down as well. There's one chapter, the next chapter, which is about alternative IO models that I'm interested in. But these other 2 chapters I'm not interested in, about terminals and pseudo-terminals. And then there's a appendix on S-trace and some other things that are interesting. So I'm excited for that. But I guess going into these last few chapters, I should keep a mindset that while terminals and pseudo-terminals aren't terribly interesting to me, that I keep an open mind. There might be something that piques my interest here. So yeah, let's go ahead and dive into it. All right, so chapter 62 on terminals. Historical users accessed a Unix system using a terminal connected via a serial line, an RS-232 connection. Terminals were cathode ray tubes, CRTs, capable of displaying characters and in some cases primitive graphics. Typically, CRTs provided a monochrome display of 24 lines by 80 columns. By today's standards, these CRTs were small and expensive. In even earlier times, terminals were sometimes hard copy teletype devices. Serial lines were also used to connect other devices such as printers and modems to a computer, or to connect to one computer to another. My understanding is like all the basic terminal input output was driven by like actually printing stuff out to a piece of paper, like a teletype printer. And so some of these early editors like Ed and even VI, but primarily Ed, a lot of the navigational aspects of it were to reduce the amount of lines output unnecessarily, because it costs paper and ink, toner or whatever, to output those characters and those lines. So if you could navigate to a place in a file, make an edit without outputting a lot of information to the printer, then that was preferable, instead of being really noisy and outputting a lot of unnecessary lines. So that was my understanding, is that early terminals were actually wired at the printers, which explains some of the optimization decisions that were made. And then also some of the output functions like print and printf or println, like those things say print in the name because it actually literally printed out to a printer so that you could see the output. So it's kind of like in the brainstem of terminals, is that everything kind of originated from that. So there's a little side here on early Unix systems. Terminal lines connected to the system were represented by character devices with the names of the form dev ttyn. On Linux, the dev ttyn devices are the virtual consoles on the system. It's common to see the abbreviation TTY derived from teletype as a shorthand for terminal. So yeah, I have a few TTYs. If we go to dev grep for TTY here, there's quite a few. The character devices. I wasn't aware that there were so many here. Like it goes up to 63. So 64 numbered, not including TTY itself, because there's zeroth. So 64 numbered, the unnumbered just dev TTY, and then there's TTY S0 through 9. So there's 10 of those. Oh no, there's these as well. So there's 32 of those. So I'm not sure what the TTYS devices are for, but I'm pretty sure these TTY devices are mapped to, like, if you hit Control Alt F1, Control Alt F2. I'm pretty sure that's what these map to, up to like 6, I think, maybe more. But I think that's what they are. I'm not sure what these are, so hopefully we learn about that soon. Alright, especially during the early years of Unix, terminal devices were not standardized, which meant that different character sequences were required to perform operations, such as moving the cursor to the beginning of the line or the top of the screen. Eventually, some vendor implementations of such escape sequences, for example, Digital's VT100 became de facto, and ultimately ANSI standards, but a wide variety of terminal types continued to exist. This lack of standardization meant that it was difficult to write portable programs that used terminal features. The Vi editor was an early example of a program with such requirements. The termcap and terminfo databases, described in Strang et al., which tabulate, I've heard of terminfo before, how to perform various string control operations for a wide variety of terminal types, and the curses library were developed in response to this lack of standardization. It is no longer common to see a conventional terminal. The usual interface to modern Unix systems is the X window system, window manager, on high-performance bitmap graphics monitor. An old-style terminal provided functionality roughly equivalent to a single terminal window, an Xterm or similar, in an X windowing system. The fact that a user of such a terminal had only a single window to the system was the driving force behind the development of the job control facilities described in section 34.7. Yeah, makes sense. Similarly, many devices, e.g. printers, that were once connected directly to a computer are now often intelligent devices connected via network. All of the above is preamble to say that the need to program terminal devices is less frequent than it used to be. Therefore, this chapter focuses on the aspects of terminal programming that are particularly relevant to software terminal emulators, i.e. Xterm and similar. It gives only brief coverage to serial lines, referring to reference for further information about serial programming are provided at the end of the chapter. Overview. By a conventional terminal, both a conventional terminal and a terminal emulator have an associated terminal driver that handles input and output on devices. In the case of a terminal emulator, the device is a pseudo-terminal. We describe pseudo-terminals in Chapter 64. Various aspects of the operation of the terminal driver can be controlled using the functions described in this chapter. When performing input, the driver is capable of operating in either of the following modes. Canonical mode. In this mode, terminal input is processed line by line, and line editing is enabled. Lines are terminated by a new line character, generated when the user presses the enter key. A read from the terminal returns only when a complete line of input is available, and returns at most one line. If the read requests fewer bytes than are available in the current line, and the remaining bytes are available for the next read. This is the default input mode. Non-canonical mode. Terminal input is not gathered into lines. Programs such as Vi, More, unless place the terminal into non-canonical mode so that they can read single characters without the user needing to press the enter key. Makes sense, like HJKL or Control U, Control D. The terminal driver also interprets a range of special characters, such as the interrupt character, normally Control C, and the end of file character, normally Control D. Such interpretation may result in a signal being generated for the foreground process group or some type of input condition occurring for a program reading from the terminal. Programs that place the terminal in non-canonical mode typically also describe processing of some or all of these special characters. A terminal driver operates two queues, one for input characters transmitted from the terminal device to the reading processes, and the other for output characters transmitted from the process to the terminal. If terminal echoing is enabled, the terminal driver automatically appends a copy of any input character to the end of the output queue, so that input characters are also output on the terminal. Subset 3 specifies the limit max input, which an implementation can use to indicate the maximum length of the terminal's input queue. A related limit max canon defines the maximum number of bytes in a line of input in canonical mode. On Linux, pathconf returns the value 255 for both these limits. However, neither of these limits is actually employed by the kernel, which simply imposes a limit of 4096 bytes on the input queue. A corresponding limit on the size of the output queue also exists. However, applications don't need to be concerned with this, since if a process produces output faster than the terminal driver can handle it, the kernel suspends execution of the writing process until space is once more available in the output queue. On Linux, we can call ioctl fd f-ion-read count to obtain the number of unread bytes in the input queue of the terminal, referred to by the file descriptor fd. This feature is not specified in subset 3. So we got a little diagram here. So we got our two queues. We got processes performing I/O that you're going to read and write to the terminal device. And there's this terminal driver that sits in between the processes performing I/O and the device itself. So if a process writes into the output queue, the terminal does its read of that output queue and displays the characters in some way. And then the terminal device might register keyboard events to type into the input queue of the process. And then if echoing is enabled, then those input characters are also displayed immediately on the output queue. Makes sense, because like when you type here, hello world, you want to see it show up as you type. mgrep tty gpg tty, I don't want that. Okay. Alright, retrieving modified terminal attributes. The tc getAddr and tc setAddr functions retrieve and modify the attributes of a terminal. TC, what does TC stand for? Okay. Allows you to get and set attributes on the terminal. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, lots of code, 25, 26, 27, 28, 29, 30, 31. 31 pages remaining on this terminal stuff. Lots of terminal stuff. The FD argument is a file descriptor that refers to a terminal. If FD doesn't refer to a terminal, these functions fail with error naughty. You're a naughty boy. Maybe no TTY. I think that's what it means. Term IOS P argument is a pointer to a term IOS structure, which records terminal attributes. So what we got here? We got some flags. Okay, just a bunch of, there's a bag of bits here to describe some terminal attributes. The first four fields of term IO structure are bit masks. The TC flag T data type is an integer type of suitable size, containing flags that control various aspects of the terminal driver's operation. I flag contains flag controlling terminal input. O flag contains flag controlling terminal output. C flag contains flag related to hardware control of the terminal line. And L flag contains flags controlling the user interface for terminal input. All the flags used in the above fields are listed in table 62.2. The C line field specifies the line discipline for this terminal. For the purpose of programming terminal emulators, the line discipline will always be set to NTTY, the so-called new discipline, a component of the kernel terminal handling code that implements canonical mode I/O processing. Setting the line description can be relevant when programming serial lines. The CC array contains the terminal special characters, interrupt, suspend, and so on, so as fields controlling the operation of non-canonical mode input. The CCT data type is a unsigned integer of suitable, unsigned integer type suitable for holding these values. And the NCCS constant specifies the number of elements in this array. We describe terminal special characters in section 62.4. The I-speed and O-speed fields are unused on Linux and are not specified in SLC3. We explain how Linux stores terminal line speeds in section 62.7. The 7th edition and early BSD terminal driver, known as the TTY driver, had grown over time so that it used no less than 4 different data structures to represent the information equivalent to the term IO structure. System V replaced this Baroque arrangement with a single structure called term IO. The initial POSIX committee selected the System V API almost as is, in the process renaming it to term IOs. Boop. When changing terminal attributes with TC setAddr, the optional actions argument determines when the change takes effect. This argument is specified as one of the following values: TCS ANOW, the change is carried out immediately. TCS AD a drain, so it's TCSA now, TCSA drain. The change takes effect after all currently queued output has been transmitted to the terminal. Normally this flag should be specified when making changes that affect terminal output, so that we don't affect options. So we don't affect output that has already been queued but not yet displayed. TCSA flush, the change takes effect for the TCS drain, but in addition, any output that is still pending at the time of the change takes effect is discarded. This is useful, for example, when reading a password where we wish to disable terminal echoing and prevent user type ahead. The usual and recommended way to change terminal attributes is to use tcgetAddr to retrieve a term IO structure containing a copy of the current settings, change the desired attributes, and then use tcsetAddr to push the updated structure back to the driver. This approach ensures that we pass a fully initialized structure to tcsetAddr. For example, we can use the following sequence to turn terminal echoing off. So we declare on the stack our term IO structure. Then we say, hey, get everything into that structure. Then we're going to negate the echo flag. And then we're going to write it out by calling tcsetAddr. And we call tcsa flush. The TC set adder function returns successfully if any of the requested changes to terminal attributes could be performed. It fails only if none of the requested changes could be made. This means that when making multiple attribute changes, it may sometimes be necessary to make a further call to TC get adder to retrieve a new terminal attribute and compare them against the requested changes. Another situation would be like read, modify, write issues. If you have concurrent code operating on the terminal device, then it might have set another set of bits into the TC set adder, the term IO structure, and thus you're going to be competing with those changes as well. There's no atomicity to this, so it's not really suitable for concurrent access. So you can maybe try to mitigate that with like going into a loop and doing multiple reads to make sure that at least at some point the state of the term IO structure is what you want. Okay. In section 34.7.2, we noted that if TC set adder is called from a process in a background process group, then the terminal driver suspends the process group by delivering the SIG TTOU signal, and that if called from an orphan process group, TC set adder fails with the error EIO. The same statement applies for various other functions described in this chapter, including TC flush, TC flow, TC send break, and TC drain. In earlier Unix implementations, terminal attributes were accessed using ioctl calls. Like several other functions described in this chapter, TC get adder and TC set adder functions are POSIX inventions designed to address the problem that type checking of the third argument of ioctl isn't possible. On Linux, as in many other Unix implementations, these are library functions layered on top of ioctl. Okay. The STTY command. The STTY command is the command line analog for the TC get adder and TC set adder functions, allowing us to view and change terminal attributes from the shell. This is useful when trying to monitor, debug, or undo the effects of programs that modify terminal attributes. We can view the current settings of all terminal attributes using the following command, here carried out on a virtual console. Okay, so we say STTY. So this is our own terminal. If we do -A, give us all the options. Huh. Okay. All right. First line of the above output shows a terminal line speed. Bits per second of the terminal window size in the line discipline in numeric form. 0 corresponds to the NTTY, the new line discipline. So when I ran this, it has new line discipline. The next three lines show the setting of various terminal special characters. The notion control C denotes control C, and so on. The string undefined means that the corresponding corresponding terminal special character is not currently defined. The min and time values relate to non-canonical mode input and are described in section 62.6. The remaining lines show the settings of the various flags from, in order, the C flag, I flag, O flag, and L flag fields of the term IO structure. The flag name is preceded by a hyphen. The flag is currently disabled, otherwise is currently enabled. When entering without command line arguments, STTY shows just the terminal line speed, the line discipline, and any other settings that deviate from sane values. We can change the settings of terminal special character using commands such as the following: STTY enter control L. Make the interrupt character control L. You can do that? That's pretty cool. STTY enter control L. And if you say sleep 100, control C, doesn't do anything, but control L not. That's pretty cool. STY, enter, Control C. There you go. Control question mark is erase. Interesting. Control question mark. How do I type in control? Come on. How do I type caret question mark in my terminal to trigger erase? Delete character. Okay. Backspace key. Okay. Kill. If I do sleep 100, Control U. What is that? Why is that? Yeah, Control U does not kill. What if we do Control W, W erase? That doesn't do anything. Control R is history searching. Control V is pasting, I think. Or what is it? No, it's just Control V. Control D, yeah. Control S is stop. Sleep 100. Okay. A lot of these I don't really think are applicable to modern terminal emulators. But it is funny that you can reassign using the syntax here. Sorry, I'm sending this to my group chat. Alright, when specifying control character as the final argument, we could do So in a variety of ways. As a two-character sequence consisting of a caret followed by a corresponding character as shown above, as an octal or hexadecimal number, or by typing the actual character itself. Good to know, good to know. If we employ the final option and the character in question is one interpreted specially by the shell or the terminal driver, then we must precede it with the literal next character, usually a control V. Although for readability, a space is shown between Control V and Control L. In the above example, no white space characters should be typed between the Control V and Control and the desired character. Sorry. It is possible, though unusual, to define terminal special characters to be something other than control characters. I'm going to do that. I'm going to mess up my terminal here. So I'm curious if it applies to multiple virtual terminals. So if I say STTY enter S, hello, we say, yeah, you can't type in sleep. Can I type in sleep here? Yeah. Sleep 100. So it only applies to that terminal if I kill it. Oh, did I kill everything? Oh, because it was a background job in that terminal. I don't like that it does that. When I open a PDF, it launches it in the background, but as a child process of the terminal. And it uses like job control. Like if I open downloads, you see it has this little job control thing here. I don't like that. But it is what it is. I'm not going to get too upset about it. But yeah, doing something like this, where you set the interrupt character to something like S, that would be massively annoying. Alright, let's continue reading. Of course, when we do this, we can no longer use the Q key for the usual purpose, i.e. generating the letter Q. To change terminal flags, such as toStop flag, you can use commands such as the following: STTY toStop, enable toStop flag, disable toStop flag. I don't know what toStop is. Sometimes when developing programs that modify terminal attributes, a program may crash, leaving the terminal in a state that renders it all but unusable. On a terminal emulator, we have the luxury of simply closing the terminal window and starting another. Alternatively, we can type the following character sequence to restore the terminal flags and special characters to a reasonable state. Control J, STTY, sane, Control J. Okay. Control J character is a real new line character, ASCII 10 decimal. We use this character because in some modes, the terminal driver may no longer map the enter key. Okay, let's try that. Control J. Hey! I didn't know Control J was another escape code for enter. That's cool. To ensure that we have a fresh command line with no preceding characters, this may not be easy to verify if, for example, terminal echoing has been disabled. The stty command operates on the terminal referred to by standard input. Using the -f option, you can, subject to permission checks, monitor and set the attributes of a terminal other than the one which the stty command is run. So we say su need privilege to access another user's terminal, and then we say, hey, I'm going to stty af on dev tty3. The F option is a Linux specific extension to the stty command. On many other Unix implementations, stty always acts on a terminal referred to by standard input. And we must use the following alternative form, which can also be used on Linux. So you just set the tty3 as the standard input. Alrighty, making progress here. Starting to get a little bit bored, although we did find a way to like mess with people by reassigning the interrupt character. Okay, table 62.1 lists the special characters recognized by the Linux terminal driver. The first two columns show the name of the character and the corresponding constant that is used as a subscript in the CC array. As can be seen, these constants simply prefix the letter V in front of the character name. The CR and NL characters don't have corresponding C _CC subscripts. Because the values of these characters can't be changed, the default setting column of the table shows the usual default value for the special character, as well as being able to set a terminal special character to specific value. It is also possible to disable the character by setting it to the value returned by the call fpathconf, where fd is a file descriptor referring to the terminal. On most Unix implementations, this call returns the value 0. The operation of each of the special characters is subject to the setting of various flags in the term.io's bitmask fields, described in section 62.5 as shown in the penultimate column of the table. The final column indicates which of these characters is specified by suspect 3. Regardless of the suspect 3 specification, most of these characters are supported on all Unix implementation internal special characters. CR, which is carriage return. Default setting is Control M. Hey, that works too. But it's a carriage return, not a line feed. Discard output, Control O. I don't know what Control O does. Skip that. End of file, Control D. Erase character, Control question mark. Interrupt, Control C. Erase line, Control U. That doesn't seem to work. Oh yeah, it does. Echo test, Control U. That's cool. I always hit Control C to erase line. Or since I'm in Vi mode, DD. The problem is that like when you're in insert mode typing, you have to go into non-insert mode to delete, and you have to go back into insert mode to type. Whereas if you're already in insert mode, you can hit Control U, and you're still in insert mode. So, yeah. Literal next, Control V. New line, Control J. Quit, which is sig quit, which is Control \. We looked at that earlier in the. I'm going to highlight some of these that are interesting. So. Erase line. They call it kill. The quit is obviously interesting there. Reprint input line. Control R. That does not do it. Bash hijacks that. Start output, stop output, suspend, erase word, control W, echo foo bar, control W. It works. The following paragraphs provide more detailed explanations of the terminal special characters. Note that the terminal driver performs its special input interpretation of one of these characters, with the exception of CR, EOL, EOL2, and NL. The character is discarded, i.e. is not passed to any reading process. Okay. Well, I'm gonna take a quick bio break here, and I'll be back to dive into each one of these special characters. Hopefully that wasn't too loud. I could hear it from the other room. The music. I need to play with some of my audio settings. Alright, so we got CR, which is carriage return character. This character is passed through the reading process. In canonical mode, iCanon, flag set, with the ICRNL, map CR to NL on input. Flag set, the default, the character is first converted to a new line, ASCII 10 decimal, control J before passing to the reading process. So it isn't carriage return by the time it hits the shell, it's just a new line. If the IGNCR ignores CR flag is set, then this character is ignored on input, in which case the true new line character must be used to terminate a line of input. An output CR character causes the terminal to move the cursor to the beginning of the line. This stuff is gonna be boring, but I'm gonna make my way through it. Because we have less than 100 or around 100 pages left. So we're gonna finish strong here. Discard is the discard output character. Although this character is defined within the CC array, it has no effect on Linux. On some other Unix implementations, typing this character once causes program output to be discarded. This character is a toggle. Typing it once more re-enables the display of output. It's useful when a program is generating a large amount of output and we want to skip some of it. This was more useful on traditional terminals where line speeds were slower than the terminal windows were. and other terminal windows were unavailable. This character is not passed to the reading process. End of file. End of file is the canonical mode end of file character, usually Control D. Entering this character at the beginning of the line causes an end of file condition to be detected by a process reading from the terminal, i.e. read returns 0. If typed anywhere other than the initial character of a line, then this character simply causes read to complete immediately, returning the character's so far input in the line. In both cases, the EOF character itself is not passed to the reading process. End of line and end of line 2. End of line and end of line 2 are additional line delimiter characters that operate like the standard new line character for canonical mode input, terminating a line of input, making it available to the reading process. By default, these characters are undefined. If they are defined, then they are passed to the reading process. The EOL2 character is operational only if the IXEN extended input processing flag is set, the default. Okay. These characters are rarely used. One application that does use them is Telnet. By sending EOL or EOL2 to the Telnet escape character, usually Control bracket, or alternatively the tilde character, if operating in R-logom mode, Telnet is able to immediately catch the character even while reading input in canonical mode. I honestly forget the sequence. It's something like tilde dot something, but there's some sequence, tilde dot enter, I think. When logged into a server over SSH, how do you kill the connection to the server via SSH input? It's tilde dot enter, I think, something, I forget. It is tilde dot. Hit enter, type tilde. It's enter tilde dot. Default escape character is tilde. It only works when typed at the start of a new line. Yeah, enter tilde dot. Oh, I didn't even know that tilde question mark was a thing. Oh, so you can suspend SSH itself, the client, versus suspending the thing that SSH is attached to, the foreground process of the shell itself. And if you want to send a little thing, you do it twice. Mathematica. How is this Mathematica? Okay. I do like Mathematica, but that is not Mathematica. Erase. In canonical mode, typing the erase character erases the previous input character on the current line. The erase character and the erase character itself are not passed to the reading process. Enter. Enter is the interrupt character. If the isig enable signals flag is set, the default typing this character causes the interrupt signal to be sent to the terminals. Foreground process group. The enter character itself is not passed to the reading process. Kill. Kill is the erase line, also known as kill line character. In canonical mode, typing this character causes the current line of input to be discarded, i.e. the character is typed so far, as well as the kill character itself are not passed through the reading process. Lnext is the literal next character. In some circumstances, we may wish to treat one of the terminal special characters as though it were a normal character for input to a reading process. Typing the literal next character, usually Control V, cause the next character to be treated literally. avoiding any special interpretation. So I could do something like, so Control C will create a interrupt on that line or whatever. But if I do Control V, Control C, oops, sorry, I might have typed that wrong. Control V, Control C. It actually types in that Control C character. So that's pretty cool. I'm gonna highlight that, literal. Next. That's pretty cool. Let's resume reading from here. Thus, we could enter the two-character escape sequence Control V, Control C to supply a real Control C character, ASCII 3, as input to the reading process. The LNext character itself is not passed to the reading process. This character is interpreted only in canonical mode with the IEXTEN extended input processing flag set, which is the default. New line. New line is the new line character in canonical mode. This character terminates an input line. The NL character itself is included in the line returned to the reading process. The CR character is normally converted to NL in canonical mode. An output NL character causes the terminal to move the cursor down one line. If the O post and O NLCR map NL to CRNL flags are set, the default then on output, a new line character is mapped to the two character sequence CR plus NL. The combination of the ICRNL and ONLCR flags means that the input CR is converted to an NL and then echoed as CR plus NL. Quit. If the ISIG flag is set, the default typing the quit character causes the quit signal, sig quit, to be sent to the terminal's foreground process group. The quit character itself is not passed to the reading process. Reprint. Reprint is the reprint input character. In canonical mode with the IEXTEN flag set, the default typing this character causes the current as yet incomplete line of the input to be redisplayed on the terminal. If this, is useful if some other programs set wall or write. Sorry, I wasn't even paying attention to what I was reading here. Reprint is the reprint input character. In canonical mode with the IEXTEN flag set, typing this character causes the current as an incomplete line of input to be redisplayed on the terminal. This is useful if some other program, e.g. wall or write, has written output that has messed up the terminal display. The reprint character itself is not passed the read process. That's pretty cool. So if I have some line here, I can say Control R, it would reprint it if there is an intermediate. I wonder how it would do that. So maybe if we do while true, and we'll do this in a subshell that is backgrounded. We say while true, do done, and here we say sleep for 5 seconds. But before we do that, we say echo foobar, sleep for 5 seconds. And then I start typing a bunch of stuff here, and then I got my foobar. If I hit Control R, it actually recapture my. So Control R kind of works to recover it. I'm gonna say this is interesting because it does work, but the shell is intercepting the Control R in this case, and using that to do the history searching. Alright, let's go and kill that. Start and stop. Start and stop are the start output and stop output characters, which operate if the enable start stop output control flag is enabled. The start and stop characters are not honored by some terminal emulators. That makes sense. Typing the stop character suspends terminal output. The stop character itself is not passed through the reading process. If the IX off flag is set to and the terminal input queue is full, the terminal driver automatically sends a stop character to throttle the input. Typing the start character causes terminal output to resume after previously being stopped by the stop character. The start character itself is not passed through the reading process. If the IXOFF enable start stop input control flag is set, this flag is disabled by default and the terminal driver had previously sent the stop character. Because the input queue is full, the terminal driver automatically generates a start character when space once more becomes available in the input queue. Yeah, sorry, I'm not keeping up here. So yeah, I don't really see this being useful, but let's continue reading. If the IX any flag is set, then any character such as not just start may be typed in order to restart output, and that character is similarly not passed to the reading process. And that character is similarly not passed to the reading process. The start and stop characters are used for software flow control in either direction between the computer and the terminal device. One function of these characters is to allow users to stop and start terminal output. This is output flow control. This is output flow control as enabled by IXON. However, flow control in the other direction, i.e. control of the input flow from the device to the computer, as enabled by IXOFF, is also important when, for example, the device in question is a modern modem or another computer. Input flow control makes sure that no data is lost if the application is slow to handle input and the kernel buffer fills up. With the higher line speeds that are nowadays typical, software flow control has been superseded by hardware, RTS-CTS flow control, whereby data flow is enabled and disabled using signals sent via separate wires on the serial port. SUSP is the suspend character. If the iSig flag is set, typing this character causes a terminal suspend signal to be sent to the terminal's foreground process group. The IUSP character itself is not passed to the reading process. So it's just Control Z. W erase is the word erase character. That's kind of cool. In canonical mode, with the I extend flag set, the default typing this character erases all characters back to the beginning of the previous word. The word is considered to be a sequence of letters, digits, and the underscore character. On some Unix implementations, a word is considered to be delimited by white space. I wonder if these are mapped to like Emacs things. So if I say, actually, you know what? I'm gonna install and launch Emacs. Sorry, I need to foreground this. Kill it. So if we say Pacman search, or I'll just say Emacs. Sure, it's available. Well, Pac-Man sees eating the dots. I love that. Emacs. What the hell? It launches a whole freaking GUI? How do I launch Emacs at a terminal without the GUI? GUIO. No window system. Okay. Emacs. No window. Okay. So we got our directional keys. If I hit Control W, does that do anything? No. What if I hit what was the other one? Kill, Control U. I'm not even like in a mode where I can like. Okay, this is not an editable file. Then can I click here? No. Welcome to GNU Emacs, one component of the GNU Linux operating system. I thought Emacs was an operating system. Control H, Emacs manual. Open a scratch buffer. Yeah, let's do that. Okay, so if I hit Control W here, does that do anything? No. Control U, no. But Control A goes to the beginning. Control E. Okay, so how do I exit? Control X, I think maybe. That's debugger. How do I exit? This buffer is for text that is not saved, and for list evaluation. To create a file, visit with Control X F. Maybe say Control X Control Q. How do I exit Emacs? Control X Control C. Okay, that's pretty close. Alright, I just wanted to test that because Emacs uses a lot of those control sequences like Control A, Control E, and I know those became shellisms. Like even in VI mode here, if I'm in insert mode typing, I can hit Control A to go. Oh no, I can't. Yeah, okay. So those are disabled when VI mode is enabled. Okay. But if I'm typing, I hit Control W or Control U, like those are terminal special characters that perform textual manipulation. I just wanted to see if those were also supported in Emacs. Looks like they aren't. All right. So we got our word erase. Other terminal special characters. Is that where we're at? Yeah. Other Unix implementations provide terminal special characters in addition to those listed in Table 62.1. BSD provides the DSUSP and status characters. The dsuspend character, typically Control Y, operates in a fashion similar to suspend character, but suspends the foreground process group only when it attempts to read the character, i.e. after all preceding input has been read. Several non-BSD derived implementations also provide the dsuspend character. The status character, typically Control T, causes the kernel to display status information on the terminal, including the state of the foreground process and how much CPU time it has consumed, and sends a SIG-info signal to the foreground process group. Does that work? Control T? Hey, no. That's Control R. Control T. I guess that's another bash fuzzy file search. If desired, process can catch this signal and display further status. Information. Linux provides a vaguely similar feature in the form of the magic sysrec key. See the kernel source file documentation sysrec for details. Systemv derivatives provide the switch character. This character is used to switch shells under shell layers. A systemv predecessor to job control. I don't really care about that. How do I trigger magic sysrq key in Linux? Holy shit, you can reboot that way? Remount file system root on kill all process except init. Show task list. So alt print string T. That did not do anything. Oh, I might. No, I don't think I need to do that. All function print screen T. No. So I want to do T to show task list. So I can say echo T. Why would I sudo T? I'm just going to echo it with a redirection. Sudo cat into proc sysrq trigger. Okay. Cat proc sys kernel sysrq 16. Okay. Disable, fully enabled, other numbers, bit masked. Interesting. I'm going to highlight the magic sys request key because I was unfamiliar with that whole system. I wasn't able to get it to work here because sometimes bit mask, I guess. But it's something I would like to potentially play around with, enabling and seeing what it's capable of. There's a lot of stuff that I highlight in this book. I imagine most of it I'm not going to revisit, but that'd be one to kind of poke around, play with. Example program listing 62.1 shows the use of TC getAddr and TC setAddr to change the terminal interrupt character. This program sets the interrupt character to be the character whose numeric value is supplied as the program's command line argument, or disables the interrupt character if no command line argument is supplied. The following shell session demonstrates the use of this program. We begin by setting the interrupt character to control L, and then verify the change with STTY. We then start a process running sleep. Find that typing control C no longer has its usual effect of terminating a process, but typing control L does terminate the process. We now display the value of the shell exit code variable, which shows the termination status of the last command. See that termination status of the process was 130. This indicates that the process was killed with signal 130 minus 128, which equals 2. Signal number 2 is SIGINT. Next, we use our program to disable the interrupt character. So you set it to undefined. Now we find that neither control C nor control L generates a SIGINT signal. We must instead use control backslash to terminate the program, which will generate a core dump, I believe. STTY is sane, return terminal to sane state. Okay, so that just uses the TC getAddr and TC setAddr, manipulating the vEnter element of the CC field of the TC termio struct. Alright, terminal flags. Table 62.2 lists the settings controlled by each of the 4 flag fields in the terminal structure. The constants listed in this table correspond to single bits, except those specifying the terminal mask, which are values spanning several bits. These may control one of the range of values shown in parentheses. Column labeled susv3 indicates whether the flag is specified in susv3. The default column shows the default setting for a virtual console login. Okay. Many shells that provide command line editing facilities perform their own manipulations of the flags instead listed in table 62.2. This means that if we are trying to use ST2Y to experiment with these settings, then the changes may not be effective when entering shell commands. To circumvent this behavior, we must disable command line editing in the shell. For example, command line editing can be disabled by specifying the command line option -- no editing when invoking bash. I think I might be catching a cold here. I don't feel too good. I'm congested. I've been sneezing. Yeah, I got a lot of symptoms. So I think I might be like worn down. I think I might need to take a break after reading this for a couple days just to recover. Not just from the book, but from whatever I'm obviously catching here. All right. Terminal flags. Okay, so these are the flag fields that we saw in that structure earlier. These aren't the CC field. These are the I flag, the O flag, and the C flag, and the L flag fields. I'm just going to read through briefly the flags that are on by default. Most of these are off. Okay. Oh shit, we're going into all these? I don't know if that's okay. They don't go. They have 2 pages on them. I think the echo thing might be important for like passwords and stuff. Like when you're typing in passwords, disable echoing of input characters. I thought that might have been a shell thing, but it looks like it's a terminal thing, which makes sense from a security perspective. You'd want to just cut it off at the terminal and not have the shell manage that security feature. All right. Several of the flags listed in table 62.2 were provided for historical terminals with limited capabilities, and these flags have little use on modern systems. For example, IUCLC and OLCOC and XCase flags were used with terminals that were capable of displaying only uppercase characters. Okay. On many older Unix systems, if a user tried logging in with an uppercase username, the login program assumed that the user was sitting at such a terminal and would set these flags, and then the following password prompt would appear. From this point on, all lowercase characters were output in uppercase, and real uppercase characters were preceded by a backslash. Similarly, for input, a real uppercase character could be specified by preceding backslash. The echo PRT flag was also designed for limited capability terminals. Various display masks are also historical, allowing for terminals and printers that took longer to echo characters such as carriage return and form feed. The related OFIL and OFDEL flags specify how such a delay was to be performed. Most of these flags are unused on Linux. One exception is the tab 3 setting for the tab DLY mask, which causes tab characters to be output as up to 8 spaces. Which causes tab characters to be output as up to 8 spaces. The following paragraph provides more details. The following paragraphs provide more details about some of the term.ios flags. Hopefully these are useful ones. Break interrupt, maybe. If the break interrupt flag is set and the ignore break flag is not set, then a int signal is sent to the foreground process group when a break condition occurs. That's like the default, right? Most conventional dumb terminals provide a break key. Pressing this key doesn't actually generate a character, but instead causes a break condition, whereby a series of 0 bits is sent to the terminal driver for a specified length of time, typically a quarter or half a second, i.e. longer than the time required to transmit a single byte. Unless the ignore break flag has been set, the terminal driver consequently delivers a single 0 byte to the reading process. On many Unix systems, a break condition acted as a signal to a remote host to change its line speed to something suitable for the terminal. Thus, the user would press the break key until a valid login prompt appeared, indicating that the line speed was not suitable for the terminal. On a virtual console, we can generate a break condition by pressing Control Break. I don't have a break key, so good luck with that. Echo. Setting the echo flag enables echoing of input characters. Disabling echo is useful when reading passwords. Echoing is also disabled within the command mode of VI, where keyboard characters are interpreted as editing commands rather than text input. The echo flag is effective in both canonical and non-canonical modes. Echo CTL. If echo is set, then enabling the echo CTL flag causes control characters other than tab, new line start and stop, to be echoed in the form of Control A, and so on. If echo CTL is disabled, the control characters are not echoed. The control characters are those with ANSI codes less than 32 plus the delete character 128 decimal. A control character X is echoed using a caret followed by the character resulting in the expression X caret 64. For all characters except del, the effect of the XOR operation is in this expansion is to add 64 to the value of the character. Thus, Control A ASCII 1 is echoed as a caret plus an A. Oh, okay. Doesn't XOR. Okay. For del, the expression has the effect of subtracting 64 from 127, yielding the value 63. For ASCII code, for question mark, so that del is echoed as caret question mark. Okay. Echo E. In canonical mode, setting the echo E flag causes erase to perform visually by outputting the sequence of backspace characters to the terminal. If echo E is disabled, then the erase character is instead echoed as question mark, but still performs its function of deleting a character. Echo K and Echo E. The Echo K and Echo E flags control the visual display when using the kill, erase line, character, and canonical mode. In a default case, both flags enabled. A line is erased visually. If either of these flags is disabled, then a visual erase is not performed. But the input line is still discarded, and the kill character is echoed. Okay, if Echo K is set, then but not Echo E, then new line character is also output. Okay, don't care. I really don't want to learn this much about terminals. So much terminal stuff. I don't want to read all this. Jesus Christ. Okay, well, we're getting through it. We're at 1305 out of 1322. So we're down to like an hour. It's probably about an hour of reading left. I could speed read this because I'm obviously not really like interested in a lot of this stuff. So I think I'll just like focus in here, speed read it, highlight anything that kind of pops up that might be useful, and then we'll get through it here. iCanon. Setting the iCanon flag enables canonical mode input. Input is gathered into lines, and special interpretation of the EOF, EOL, EOL2, erase, LNext, kill, reprint, and W erase characters is enabled. But note the effect of the iExtend flag described below. iExtend. Setting the iExtend flag enables extended processing of input characters. This flag is also known as iCanon. This flag, as well as iCanon, must be set in order for the following characters to be interpreted: EOL2, LNext, reprint, and W erase. The iExtend flag must also be set for the IUCLC flag to be effective. SOC 3 merely says that the iExtend flag enables extended implementation defined functions. Details may vary on other Unix implementations. IMAX-Bell on Linux, the setting of the IMAX-Bell flag is ignored. On a console login, the bell is always running when the input queue is full. IUTF-8, setting ITF-8 flag enables cooked mode, section 62.6.3. So that's in the next section. To correctly handle UTF-8 input when performing line editing. No flush. By default, when a signal is generated by typing interrupt, quit, or suspend character, any outstanding data in the terminal input and output queues is flushed, discarded. Setting the no flush flag disables such flushing. OPOS, setting the OPOS flag enables output processing. This flag must be set in order for any of the flags in the CEO flag field of the terminal structure to be effective. But conversely, disabling OPOS flags prevents all output processing, post-processing. Okay, a bunch of different flags here. Concerned with generating, with parity, generation, and checking, which is not something I care about. I'm going to skip over that. Example program, I'm going to skip over as well because I don't really care about that. It just uses this system call here, TC set editor, which you've already seen. Okay, let's read a little bit about terminal modes. At least there's a lot of code that we can skip over. Terminal identification at the end of the chapter would be useful. We see that a lot. I mean, you're familiar with it already, but it'd be useful to review. Okay, so terminal I/O modes. We have already noted that the terminal driver is capable of handling input in either canonical or non-canonical mode, depending on the setting of the iCanon flag. We now describe these two modes in detail. We then describe three useful terminal modes, cooked, cbreak, and raw, that are available in 7th edition Unix, and show how these modes are emulated on modern Unix systems by setting appropriate values in the term I/O structure. Canonical mode. The canonical mode input is enabled by setting the iCanon flag. Terminal input in canonical mode is distinguished by the following features. Input is gathered into lines, terminated by one of the line delimited characters, new line, end of line 2. If the IExtend flag is set, EOF at at anything other than the initial position in the line, or CR, except in the case of EOF, the line delimiter is passed back to the reading process as the last character in the line. Line editing is enabled so that the current line of the input can't be modified. Thus, the following characters are enabled: erase, kill, and if the IExtend flag is set, W erase. The IExtend flag is set, the reprint and LNext characters are also enabled. In canonical mode, a terminal read returns when a complete line of input is available. The read itself may fetch only part of that line. If it requested fewer bytes, remaining bytes will be fetched by subsequent calls to read. A read may also terminate if input by a signal handler and restarting of system calls is not enabled for the signal. While describing the no flush flag in section 62.5, we noted that the characters that generate signals also cause the terminal driver to flush the terminal input queue. This flushing occurs regardless of whether the signal is caught or ignored by an application. We can prevent such flushing by enabling the no flush flag. Non-canonical mode. Some applications, e.g. VI and less, need to read characters from the terminal without the user supplying a line delimiter. Non-canonical mode is provided for this purpose. In non-canonical mode, ICANN unset, no special input processing is performed. In particular, input is no longer gathered into lines, but is instead available immediately. In what circumstances does non-canonical read complete? We can specify that a non-canonical read terminates after a certain time, after a certain number of bytes have been read, or both in combination. Two elements of the term-IOCC array determines behavior: time and min. Time element indexing using the constant vtime specifies a timeout value in tenths a second. The min element index with the vmin specifies the minimum number of bytes to be read. The min and time setting have no effect on canonical mode terminal I/O. The precise operation and interaction of the min and time parameters depends on whether they each have non-zero values. The four possible cases are described below. Note that in all cases, if the time of a read, sufficient bytes are already available to satisfy the requirements specified by min, read returns immediately with the lesser of the number of bytes available and the number of bytes requested. Min is equal to 0, time is equal to 0, which is polling read. If data is available at the time of the call, then read returns immediately with the lesser of the number of bytes available and the number of bytes requested. If no bytes are available, read completes immediately, returning 0. This case serves the usual requirements of polling, allowing the application to check if input is available without blocking if it's not. This mode is somewhat similar to setting the non-block flag for the terminal, while in canonical mode, however, with non-block, if no bytes are available for reading, then read returns -1 with array again. Min is greater than 0, but time is 0, blocking read. The read blocks potentially indefinitely until min bytes are available and returns up to the number of bytes requested. Programs such as less typically set min to 1 and time to 0. This allows the program to wait for a single key press without needing to waste CPU time by polling in a busy loop. If a terminal is placed in non-canonical mode with min set to 1, the time is set to 0. Then the techniques described in Chapter 63 can be used to check whether a single character rather than a complete line has been typed at the terminal. Min is equal to 0, time is greater than 0, read with a timeout. Timer is started when read is called. The call returns as soon as at least 1 byte is available, or when time tenths of a second have elapsed. In the latter case, read returns 0. This case is useful for programs talking to a serial device, e.g. a modem. The program can send data to the device, then wait for a response using a timeout to avoid hanging forever in the case the device doesn't respond. Min is greater than 0, time is greater than 0. Read with interbyte timeout. After the initial byte of input becomes available, a timer is restarted for further byte is received. The read returns when either the lesser min bytes and the number of bytes requested has been read, or when the time between receiving successive bytes exceeds time tenths of second. Since the timer is started only after initial bytes become available, at least one byte is returned. Your read can block indefinitely for this case. This case is useful for handling terminal keys that generate escape sequences. For example, on many terminals, the left arrow key generates a 3-character sequence consisting of escape followed by control D, or bracket D. These characters are transmitted in quick succession. Applications handling such sequences need to distinguish the pressing of such a key from a situation where a user slowly types each of the characters individually. This can be done by performing a read with a small interbyte timeout, say 0.2 of a second. Such a technique is used in the command mode of some versions of VI. Depending on the length of timeout in such applications, we may be able to simulate a left arrow key press by quickly typing the aforementioned 3-character sequence. Portably modifying and restoring min and time for historical compatibility with Unix implementation, SOSI3 allows the values of vmin and vtime constants to be the same as veof and veol respectively, which means that these elements of the term IOCC array may coincide. On Linux, these values of these constants are distinct. This is possible because veof and veol are unused in canonical mode. The fact that vmin and veof may have the same value means that caution is needed in a program that enters non-canonical mode, sets min typically 1, and then later returns to canonical mode. Return to canonical mode, EOF will no longer have its usual value of ASCII 4 control D. The portable way to deal with this problem is to save a copy of the term IO settings prior to changing to non-canonical mode, and then use this save structure to return to canonical mode. I wonder, is this like kind of like alternate mode? They call it non-canonical mode in the book here, and I'm sure that's the technical name for it. But I've seen alternate mode in terminals like GhostT. What is the difference between non-canonical mode terminals and what is referred to as alternate mode? Canonical versus non-canonical mode, also known as raw C break. This is a line discipline setting in the kernel TTY driver. It controls how input is delivered to the program. You toggle it with term IOs, ST2I, C, yeah, okay. Canonical mode, non-canonical mode, alternative screen buffer. This is not a kernel TTY mode at all. It is a feature of terminal emulators, xterm, gnome terminal, etc., controlled by ANSI escape sequences. When a program enters the alternate screen, terminal switches to a separate screen buffer. The normal scroll back is hidden. The screen starts blank. When the program exits, the original screen is restored. It looks like nothing happened. We'll use vim plus man htop tmux. This is strictly about what gets displayed, not input handling. Okay. Why programs use both together? Most TUIs do switch to alternative screen, switch terminal to non-canonical mode, draw UI, plus read keystrokes live, restore both on exit. Example, vim, non-canonical, so it can react to each key press instantly. Alternative screen, so your shell screen comes back after quitting. Quick demos, canonical, non-canonical. Show alternative screen manually. Mental model is canonical mode, how the keyboard input pipeline behaves. Non-canonical mode, raw key stream delivery, alternate screen, a temporary visual canvas. Is alternate mode available on regular serial console style terminals? Like if I hit CTRL plus Alt plus F6 or say F4 on Linux. I'm gonna say no. This is not a terminal emulator. It's the kernel's built-in VT subsystem. Does not implement a true alternative screen buffer. No op. Raw virtual console. Vim will still work fine, but there's no real hidden previous screen. What you see may just get overwritten. Okay. When you exit, program redraws or clears the screen, but there's no emulator managed buffer to restore. Tools like Vim and Less don't rely solely on alt screen. They often clear the screen on entry, redraw on exit, manually repaint the prompt. So again, look like an altered screen behavior when none exists. Oh, that's what the S0 is serial. All those S things are serial devices. Okay. Makes sense. Cooked, C-break, and raw modes. So we got that. We got like a page to read on that, and a bunch of code we're going to skip. An explanation for the code that we're going to skip. We'll read the demo of the use of the program. Then we got terminal line speed bit rates. That's like a page and a half. Terminal line control, which is about a page and a half. Terminal window size, which actually might be useful. And then terminal identification. Okay, so we're getting through it. We're getting through it. This is more than I ever wanted to know about terminals, though. Alright, so cooked, C-break, and raw modes. The terminal driver in 7th edition Unix, as well as early versions of BSD, was capable of handling input in 3 modes: cooked, C-break, and raw. The difference between the 3 modes are summarized in table 62.3. Cook mode was essentially canonical mode with all the default special character processing enabled. Raw mode was the converse, non-canonical mode with all the input and output processing as well as echoing switched off, an application that needed to ensure that the terminal driver makes absolutely no changes to the data transferred across the serial line would use this mode. C-break mode was intermediate between cooked and raw modes. Input was non-canonical, but signaling generated characters were interpreted, and the various input and output transformations could still occur depending on the individual flag settings. CBreak mode did not disable echoing, but applications employing this mode would usually disable echoing as well. CBreak mode was useful in screen handling applications such as LESS that permitted character by character input, but still needed to allow interpretation of characters such as interrupt, quit, and suspend. Example setting raw mode and CBreak mode. In the 7th edition of the original BSD terminal drivers, it is possible to switch to raw or CBreak mode by tweaking single bits in the terminal driver data structures. With the transition to POSIX, terminal IOS interface, now supporting all Unix implementations, single bits for selecting raw and CBreak mode are no longer available. The applications emulated in these modes must explicitly change the required fields in the terminal IOS structure. Listing 62.3 provides two functions, set TTY set CBreak and TTY set raw, that implement the equivalents of these terminal modes. Applications that use the ncursive library can call functions CBreak and raw, which perform similar tasks to our functions. Okay, I don't want to dive into the details of this stuff. Okay. We can skip over this. All this code and go to the example. Here's an example of what we see when we ask the program listing 62.4 to use raw mode. So initial terminal mode is sane, cooked. Then we say test TTY functions. Then it's craziness. And then in the last line of the preceding shell session, we see that the shell printed its prompt on the same line as the Q character that caused the program to terminate. The following shows an example of run using CBreak mode. Okay. Terminal line speed, bit rates. I don't really care about this stuff. I'm going to skip over it. Terminal line control. Don't really care about this. Terminal window size. I might actually care about this. In a windowing environment, a screen handling application needs to be able to monitor the size of the terminal window so that the screen can redraw appropriately if the user modifies the window size. The kernel provides two pieces of support to allow this to happen. The SIG-winch signal is sent to the foreground process group after a change in terminal window size. By default, the signal is ignored. At any time, usually following a receipt of SIG-winch signal, a process can use the ioctl TIOCG-WIN-SZ operation to find out the current size of the terminal window. Ioctl operation is used as follows. So we read into a data structure called win-size. The FD argument is a file descriptor referring to the terminal window. The final argument to ioctl is a pointer to win-size structure used to return the terminal win-size. Like many other implementations, so we got row call x pixel and y pixel, number of rows, number of columns, horizontal size, vertical size. Okay, that's cool. Like many other implementations, Linux doesn't use the pixel size fields of the win-size structure. It makes sense. Listing 62.5 demonstrates the use of the SIG-winch signal and the octal operation. The following shows an example of output produced when the program is run under Window Manager and the terminal window size is changed 3 times. So it actually catches SIG-winch and then outputs the information. It's a pretty simple program. It just goes into a for loop, calls pause to wait for the signal handler. Signal handler is actually empty. It just used to resume. So we set our disposition up here to the empty handler. And then when we resume, we just read out and then go back to pause. Makes sense. It is also possible to change the terminal driver's notion of the window size by passing an initialized win size structure to an octal operation. Oh, so you can run it if the new values in the win size structure differ from the terminal driver's current notion of the terminal window size, two things happen. Terminal driver data structures are updated using the values supplied in the WS argument. A sig-winch signal is sent to the foreground process group of the terminal. Note, however, that these events on their own are insufficient to change the actual dimensions of the displayed window, which are controlled by software outside the kernel, such as a window manager or a terminal emulator program. Although not standardized in SUSV3, most Unix implementations provide access to the terminal window size using the ioctal operations described in this section. Terminal identification. In section 34.4, we describe the ctermid function, which returns the name of the controlling terminal for a process, usually dev tty on Unix systems. Functions described in this section are also useful for identifying a terminal. The isAddy function enables us to determine whether a file descriptor is associated with a terminal as opposed to some other type. The isAddy function is useful in editors and other screen handling programs that need to determine whether their standard input and output are directed to a terminal. Given a file descriptor, the tty_name function returns the name of the associated terminal device. To find the name of the terminal, tty_name uses opendir and readdir functions described in section 18.8 to walk through the directories holding terminal device names, looking at each directory entry until it finds one whose device ID field of the stat structure matches that of the device referred to by the file descriptor. Terminal device entries normally reside in two directories, dev and pts. The dev directory contains entries of virtual consoles and BSD pseudo-terminals. The dev PTS directory contains entries for the systemv pseudo-terminal slave device. We described pseudo-terminals in chapter 64. A rancid version of tty_name exists in the form of tty_name_r. The tty command, which displays the name of the terminal reference to the standard input, is the command line analog of tty_name. Yay, we're done with this chapter. I had to skip over some of it because it's just not useful at all to me. But let's read the summary here. On early Unix systems, terminals were real hardware devices connected to a computer via serial lines. Early terminals were not standardized, meaning that different escape sequences were required to program the terminals produced by different vendors. On modern workstations, such terminals have been superseded by bitmap monitors using the X windowing system. However, I'm using Wayland. I don't know what you're talking about, X windowing system. However, the ability to program terminals is still required when dealing with virtual devices, such as virtual consoles and terminal emulators, which employ pseudo-terminals, and real devices connected via serial lines. Terminal settings, with the exception of the terminal window size, are maintained in a structure of type termios, which contains 4 bitmask fields that control various terminal settings, and an array that defines the various special characters interpreted by the terminal driver. The tcgetAddr and tcsetAddr functions allow a program to retrieve and modify the terminal settings. When performing input, the terminal driver can operate in 2 different modes. In canonical mode, input is gathered into lines. I think one thing I now realize is that I can run this was it stty sane? Yeah. Where did he run that? Could have sworn he ran that somewhere. Trying to find it here. All right. don't see it anywhere here, but I know he ran it somewhere. Here it is. STTY sane. So if my terminal ever gets messed up again, like I think I've had it happen where like, let's actually try to mess up a terminal here. So I'm just gonna open Vim here, or lazy Vim, and then I'm opening another terminal and I'll ps aux grep for nvim, which will give us the grep, the embed, and then this guy here. So these two processes, kill -9, that. You see how it like screws up the terminal? But I can type in STTY sane, clear. Let's try doing this again. So we got this guy here, kill 9 that, which left it in this weird state. I can just clear it though. I'm trying to get like a program that really messes up the terminal. Maybe try less. Dev u random. Yeah, why not? Okay, now we say, wow, it's not letting me get out of this terminal here. If I hit command right, no, it doesn't want to get me. Okay, maybe that was a bad idea. Let's do less of like, or echo foo bar into temp foo, less that thing. Okay, so we got some stuff here, and then I'm gonna say, why is this thing, look at this, it's all, it won't let me escape my terminal. Look at this, I've never seen this before. STTY, maybe if I STTY sane that, I'm gonna kill it. Okay, that lets me escape. I don't know. I was trying to use STTY sane to like reset the terminal mode to recover. I've had situations before where the terminal just gets completely messed up. I was trying to simulate that by killing Vim, but that didn't do anything. Less temp foo. Okay, I can escape it now. Sorry, less. Now if I ps aux grep for less, and that's Wayland stuff. This is what I want here. I'll kill 9 that. I still have my shell there. Okay. I don't know. Messing up my terminal is not a thing that I can easily reproduce. And I won't remember this STTY sane thing next time it happens. So, unfortunately, I don't think I'm going to get much use out of it. Anyways. Usually I just restart the terminal anyways when that happens. Terminal settings, with the exception of terminal window size, are maintained in a structure called termios, which contains 4-bit mask fields that control various terminal settings, and an array that defines the various special characters interpreted by the terminal driver. The tcgetAddr and tcsetAddr functions allow a program to retrieve and modify the terminal settings. When performing input, the terminal driver can operate in 2 different modes. In canonical mode, input is gathered into lines terminated by one of the line delimited characters, and line editing is enabled. By contrast, non-canonical mode allows an application to read terminal input a character at a time without needing to wait on the user to type a line delimited character. Line delimiting is disabled in non-canonical mode. Completion of a non-canonical mode read is controlled by the min and time fields in the term.io structure, which determine the minimum number of characters to be read and a timeout to be applied to a read operation. We describe 4 distinct cases for the operation of non-canonical reads. Historically, the 7th edition and BSD terminal drivers provided 3 input modes: cooked, cbreak, and raw, which performed varying degrees of processing of terminal input and output. Cbreak and raw modes can be emulated by changing various fields within a term.io structure. A range of functions perform various other terminal operations. These include changing the terminal line speed and performing line control operations, generating a break condition, pausing until output has been transmitted, flushing terminal input and output queues, and superseding or resuming transmission of data in either direction between the terminal and the computer. Other functions allow us to check if a given file descriptor refers to a terminal, and to obtain the name of that terminal. The ioctl system call can be used to retrieve and modify terminal window size recorded by the kernel, and to perform a range of other terminal related operations. Okie dokie. Not doing any of those exercises. Alright, finally, we are at the greatest chapter of the book, chapter 63, which is alternative I/O models, the one that I actually care about. And we got lots of stuff here. Lots of interesting stuff. It's probably like, how many pages is this? Okay, so 1374 and 1326, so around 50 pages. 1374, 1326, 48 pages. So we got 50 pages of that. And then how much on pseudo terminals? Is that going to be... Okay, excluding the exercise, which I won't be doing. 1397. 1376. 1376. So that's 21 pages. Less than half. Trying to think of like what I want to tackle here. If I want to just get all the pseudo terminal stuff out of the way. Which leaves nothing but really enjoyable content with chapter 63. Or if I want to just continue on the good stuff right now. Chapter 63 looks intimidating, to be honest. It's 48 pages of really interesting stuff, but stuff that I'm not terribly familiar with. Like, I've never written a C program with select and pull and epoll and all this stuff. I've written a bunch of Go programs, and Go has a select statement that, from what I understand, is similar to the select system call, where you select and basically select will pause, or I guess you say block, until one of its channels are ready to be read from. Whereas the select system call will, I think, block until one of the file descriptors is available to be read from that you're selecting from. And in Go, there's a select statement, but there's also a dynamic select function. So I think select function has like a variadic number of... Actually, let's just pull it up. Golang dynamic select. Who says Stack Overflow is not useful? Yeah, this thing here. You can have a select case, which is an array, so it's not variadic. And then it blocks until it returns these values. Cool. All right, I think I'm gonna just go into the alternative IO modes chapter. I'm gonna take a break here. I gotta start a little bit early. It's been 2 hours, so I'm gonna take a little bit of a break. Get some food. I may take an early lunch. Then when I get back, I'll start on the alternative IO models chapter, which is the best chapter of the book. So this is what I've been waiting for. I'm excited for this. Cool. All right. I will be back in a couple hours here.